Funding for this program was provided by the Annenberg CPB project.
I thought it was time this class had some class. Actually, these days, scientists are pretty informal people. It's certainly rare to see one dressed like this. But in the 19th century, it was not uncommon for formal lectures to be given in formal attire. And there's no place that was more true than at the famous Royal Institution. I have here a picture that was made in the middle of the 19th century. This particular public lecture seemed worth immortalizing in a picture because it was attended by the Prince of Wales. This, after all, was the Royal Institution. The Prince of Wales, presumably, is one of these chaps here in the front row. I'm not sure which one. But the reason that this lecture is worth remembering today is not because it was attended by the Prince of Wales. It's because the lecturer was Michael Faraday. In fact, it was at a lecture just like this one, nearly 200 years ago, that the young Michael Faraday became so entranced with science that he decided to give up his promising career as an apprentice bookbinder. But in that series of lectures, there is one man who made a lasting impression on the entire tradition. His name was Charles Wheatstone, and he was a key figure in working out the nuts and bolts that made electricity practical. And those nuts and bolts are our subject for today.
The nuts and bolts that hold together the complex machinery of the modern world are no more important in the history of civilization than the simple flow of water. Learning to control and harness the flow of water has been a critical ingredient in the development of civilization. It was no accident that the earliest civilizations developed along the banks of the great rivers, the Nile, the Tigris, and Euphrates, the great water circuits of nature. In order to flourish, every society had to develop the means to manipulate, control, and distribute the flow of water for irrigation, for the draining of swamps, and to nourish the growth of cities. Just as all roads led to Rome, so did an ingenious network of aqueducts. The empire survived as long as it did, to a large degree, because the aqueducts brought down fresh water from the hills of Albanus. In their time, those complex circuits of pipes that distributed water to the city's baths, buildings, and fountains were amazingly sophisticated. But only in the last century did another flowing technology begin to develop: electricity. Inventors such as Thomas Edison found ways to manipulate electric currents to light lamps in houses and to carry dots and dashes long distances through wires. They also created ways to generate and distribute electricity in ever more complex grids. But in the days since Edison's illuminating station was the world's premier power plant, engineers have developed much more subtle ways to use the flow of electricity. Today, a single computer chip contains an electric circuit as complex as the street map of an entire city. And in principle, the very existence of a major city such as Los Angeles depends on many of these circuits. LA is, of course, more than a freeway. But without an engineering miracle, it would be no more than a dusty village between the desert and the deep blue sea. And that miracle is called the Metropolitan Water District. Whether designing water circuits or electric circuits, it all boils down to controlling the flow of currents. 163,000 cubic meters of water per hour flow through the Colorado River aqueduct toward the Los Angeles basin. 1.3 amps of electric current flow through this copper wire. Just as water makes life possible, the flow of electricity makes light possible. How much light depends on the amount of current, which is measured in amps. 1 amp is 1 coulomb of electric charge per second flowing through a circuit. In other words, electric current, I, is the rate of flow of electric charge, Q. At any instant, this current is the same everywhere along the wire. Because electric charge, like water, is neither created nor destroyed along the way. It just keeps flowing along. While rivers have flowed for thousands of years, electricity was basically a static field until 1800. That was the year Alessandro Volta charged ahead and invented the battery. This new source of power, called the voltaic pile, made a sustained flow of electricity possible and opened the floodgates of progress. With it, Sir Humphrey Davy soon extracted brilliant new metals, sodium and potassium, from the common salts soda and potash. A few years later, Hans Christian Ørsted deflected a magnetic needle with nothing but the current from a voltaic pile, and so discovered electromagnetism. Later, in the 19th century, Thomas Edison used the continuous flow of electric current provided by a voltaic pile to develop the first electric lamp. He also used that current to perfect a device invented by others, the telegraph. Much earlier, Carl Friedrich Gauss had seen the potential in Ørsted twisted compass needle. An electric switch closed in one place could cause a magnet to move in another place. Others soon came to the same realization. The telegraph held the promise of almost instantaneous long-distance communication. But in the beginning, the promise of long-distance calling was short-lived. After traveling a few kilometers, the signal was too weak to activate the magnetic device. That problem was solved by Charles Wheatstone, a musical instrument maker and a student of acoustics. He found the solution to this dilemma in the almost unintelligible writings of an obscure German professor named George Simon Ohm. What Ohm had predicted with abstract mathematical reasoning, Wheatstone showed through direct experiment. The signal can be kept the same size if the voltage is increased in proportion to the distance. Wheatstone had verified the rule known as Ohm's law.
To make a current flow through a conducting material, a voltage is needed. The current is always proportional to the voltage. The constant of proportionality is called the resistance. This equation is known as Ohm's law. An element in an electric circuit with resistance is called a resistor.
Ohm's law isn't a fundamental law of nature like Newton's second law or the law of conservation of energy. It doesn't hold in all situations, but it's a very useful rule in most practical situations. And it helped turn the telegraph into a very practical invention indeed. With Edison's refinements and the code devised by Samuel Morse, the telegraph pushed back the American frontier and took the train with it. Telegraph wires paralleled the tracks, and the information they carried was essential to the smooth running of the entire railroad system. Not that there wasn't resistance to the use of both of these inventions. People said electricity was dangerous, and some said that at the fast speeds trains could travel, humans wouldn't be able to breathe. But there was no stopping progress. And in the long run, wires and rails together played the same vital role rivers had long played, transporters of people, cargo, and ideas. And through miles and miles of wire, the flow of information follows from the practical use of Ohm's law. And in much the same way, similar rules lead hydraulic engineers in the design and operation of aqueducts. Those engineers have long known that the rate at which water flows through a pipe depends on just a handful of factors. The slope of the land and the pressure applied, the length and diameter of the pipe, and the viscosity and density of water. In precise analogy, the amount of electric current that flows through a resistor depends on the voltage drop across it, how wide and how long it is, and what it's made of.
The resistance of an electric resistor is proportional to its length, inversely proportional to its area, and proportional to its resistivity, or its tendency to inhibit the flow of electrons. This tendency to resist is something all materials have, but to varying degrees. Adding resistors to a circuit, one after another, has the same effect as making one resistor longer. These are called resistors in series. Putting resistors side by side increases the area through which the current can flow. These are called resistors in parallel, and they have a lower resistance than either one alone.
The same is true of water. Adding sections of pipe in a series is the same as making it longer, and so the resistance to movement increases. But if the pipes are added side by side, they can carry more water more easily. And these particular pipes carry a lot of water, lifting it up 1,600 feet from the Colorado River to a point where it can flow down to Los Angeles. However, because the dam and pumping station were designed to carry away so much water, the project itself encountered some stiff resistance, especially from Arizona, the state which happens to be on the other side of the river. On the day construction began in 1934, the Arizona State Militia perched on the rim of the river with rifles and machine guns. In this case, the basis for resistance was clear. The flow of progress for California was at the expense of Arizona's future. But what about the natural resistance to the progress of electrons? Just what is the nature of electrical resistance? Under the influence of an electric field, electrons move through a metal much as a marble falls through a viscous fluid. If it weren't for resistance, they would accelerate freely, like a falling body in a vacuum. But as it is, they move on the average at a constant speed. Resistivity is like viscosity. The more of it a material has, the slower a particle will move through it. But what slows the electrons down? In other words, in a conductor, what resists the flow of electricity? Inside a metal, electrons constantly move in all directions. Here, just a few of them are represented as dots. They orbit through the metal as if it were one giant molecule. This kind of flow encounters no resistance, nor does it create a net flow in one end and out the other. Under these conditions, the conductor is in electrostatic equilibrium. There's no electric field inside, no voltage difference from one end to the other. But if a battery makes an electric current flow, equilibrium is destroyed, and an electric field is created inside the conductor. Inside a perfect crystalline metal, if a sample of it could be found, the mobile electrons would continuously accelerate, like a penny falling in a vacuum. But in the real world, crystals aren't perfect. They have defects and impurities, and their atoms vibrate with thermal energy. Electrons, accelerated by the force of the electric field, bounce off each imperfection, behaving somewhat like a ball in a pinball machine. All that bouncing, all that stopping and restarting produces the resistance that prevents the electron flow from building up speed. So the electrons move at a constant average speed, creating a constant current under the influence of a constant force. As the electrons bounce off the imperfections, they set the atoms into larger vibrations. So the electrical energy of accelerated electrons turns into the heat energy of vibrating atoms. And about 100 years ago, a brilliant idea rose from that heat. If a resistor gets hot enough, it will glow. And Thomas Edison found just the right materials that would glow brightly. Of course, all circuits don't glow, but they all produce heat, whether it's wanted or not. In computers, for instance, fans are used to eliminate unwanted heat. In fact, some supercomputers generate so much heat that they require a liquid cooling system to keep the temperature down. Whether heat is the goal or an unwanted byproduct, it takes power to produce it.
As current flows through a resistor, the energy that's turned into heat is equal to the amount of charge that flows times the change in potential. The rate of heating, or power consumed, is equal to the current times the voltage. Using Ohm's law, the power can also be written as I squared R or V squared over R.
And what's the result? Well, to start with, it's measured in watts. 1 watt is a measure of power equal to 1 amp times 1 volt. Multiply that watt by 1,000 to get kilowatts. Multiply that by 1,000 again to get megawatts. At peak hours, Parker Dam generates 120 megawatts. watts and water, the electric grid and the water system. It's a powerful analogy that takes concrete shape here in this hydroelectric generating plant. If progress rides the currents of water and electricity, it also demands a lot of each. In America's energy-hungry society, each person consumes about a kilowatt of electric power all the time, day in and day out, all year long. And each family consumes about an acre-foot of water. That is, all the water in 1 acre of land covered to a depth of 1 foot every year. To deliver both water and power to the consumers, engineers must first master the art and science of circuit design. The common elements of elementary electric circuits are wires and switches, batteries, resistors, and capacitors. And while these elements can be combined into networks of ever-increasing complexity, they always obey the same simple rules, called Kirchhoff's laws. Gustav Kirchhoff, a German physicist, was keen on mathematics. By applying Ohm's law and generalizing it fully, he derived 2 laws, and each expresses a familiar idea. One of those ideas is conservation of charge. And the corresponding law for circuits is, whenever one current splits into 2, or vice versa, the total current into the junction will equal the total current out of it. Kirchhoff's other law expresses conservation of energy. An electric charge going around any complete circuit neither gains nor loses energy. Consider an electric charge in space, not confined to a circuit. If it's moved through space on a path that brings it back to its starting point, no net work is done. The electric potential, or voltage, may go up or down, but it always gets back to where it started, and the same is true inside a circuit. Notice that an integral along a closed path has a special notation, an integral sign with a circle on it. So, in the special case of an electric circuit, all the voltage rises due to batteries and charged capacitors, and all the voltage drops due to currents flowing through resistors add up to 0. Using these 2 laws alone, engineers analyze the most complex circuits. To take just a simple example, consider a capacitor connected to a resistor and a battery. Even as the capacitor charges, the total rise in voltage equals the total fall around the circuit. A capacitor in an electric circuit stores charge, much the same way a reservoir stores water for later use. And it takes time to fill or empty either one. How much time? That depends, of course, on how big the reservoir is and how much resistance there is to the water flowing out. The bigger the reservoir and the more the resistance, the longer it will take. Exactly the same is true of charge draining from a capacitor. And applying Kirchhoff's laws, the time is found to be equal to the capacitance times the resistance. Of course, there are no immediate plans to drain Lake Havasu. As fast as water is drained to quench the thirst of Los Angeles, snow from distant mountains melts to feed the Colorado, which in turn refills the reservoir, as part of a global cycle that conserves moisture, much as electric circuits conserve charge. And so to the notion of progress is added the principle of conservation, perhaps proving that the more things change, the more they stay the same. Civilization still depends on currents, though the flow of electricity has been added. And the modern city, as much as ancient Rome, depends upon and is limited by the ability to channel and distribute those currents.
Today, we've studied the rules that make electricity practical. They were first worked out by people named Ohm and Kirchhoff and Charles Wheatstone. Wheatstone himself was revered by his colleagues in his own time, but he was unknown to the public. He was a shy man and morbidly timid in front of an audience, just like me. In fact, that was the way in which he managed to change the tradition of public lectures at the Royal Institution. Apparently, one evening in 1846, it was Charles Wheatstone who was to give that evening's public lecture. But at the very last second, with the audience already waiting in their seats, Wheatstone panicked and fled, leaving nobody to give the lecture. Well, Michael Faraday stepped in and gave a brilliant impromptu lecture speculating that light might be some kind of a disturbance of electricity and magnetism, an idea that turned out to be exactly right many years later. That tradition of public lectures at the Royal Institution continues to this very day. Every Friday evening at 8 o'clock on the dot, a celebrated scientist, dressed just like this, in formal attire, steps out before a glittering audience to deliver a lecture on the latest developments in science. But for a half hour before the lecture, that scientist has been kept locked in a little room to make sure that he doesn't do a Wheatstone and run away at the very last minute. And that's the reason that I was kept locked in that room until the beginning of this lecture. I'll see you next time.
Funding for this program was provided by the Annenberg CPB project.